Welcome to part 2 of the notes. For the next problem, it's going to be a little bit trickier. We can do this. Believe in this. Okay. There we go. All right, this is going to be the canoe problem. But you see these a lot with center of mass. So we'll write it out. So we have a person in a canoe. We have a 30-kilogram canoe. Our canoe is 6 meters long. And so the man is initially 1 meter from the end, from the left end of the canoe, and he walks to the other end. Very exciting. So he stands up, they're on the water, and he walks from one end from the left side to one end from the right side. We're going to assume there's no friction between the canoe and the water. So it is free to move under him. So I want to know, how far does the canoe move under him? So let's try and visualize this a little bit. Okay, so he starts, let's draw our canoe, and he's like over here. Okay, so 1 meter from one end. And he ends up, well, let's not draw the canoe yet. So that's where he starts off. A couple things we need to know is that, so right now our center of mass, it's going to be, if it was just the canoe, it would be right in the middle of the canoe. But now since we have the guy in there too, it's going to be closer to the person. So we'll say, we're going to draw a line all the way down, and that is the position of the center of mass of the man-canoe system. So the position of the center of mass of the two is not going to change. That's going to stay fixed. Okay, why? Well, because there's no external net force applied to our canoe man system. Okay, so the man pushes on the canoe pushes on the man, but there's nothing outside to make the canoe man move in space. So the center of mass is going to stay right there, stay fixed in space. So as he walks to the right, okay, so say he's 1 meter from the end. So when he's like at the center of mass, well, that must be he must be at the midpoint of the canoe, because now that is the center of mass of the canoe and the man. So now he's at 3 meters from, we'll call the left end 0. Okay, so you can see the canoe has shifted backwards. So thinking back to Newton's third law, to move forward, there needs to be a force on the man, so the canoe is pushing him forward as he pushes back on the canoe. So there are internal forces, they just cancel each other out. and they make him move forward, but the canoe is moving back. So then he keeps walking forward until he's a meter from the other end. But if we leave our reference point as the left end of the canoe, well, we can see he's 5 meters from that end because it's a 6 meter long canoe. So you can see that we're going to use the end of the canoe as a reference. Because we don't have a shore or another boat or anything else to use as a reference. So in those cases, just use one of the objects as a reference point. Okay, so then we'll have the question, well, how far away is the canoe from the end of the canoe? Okay, for the astronaut problem, we just said, well, the astronaut as a whole is 0 meters away from himself. That's not going to work as well here. So how far is end of canoe from the canoe? Asking the deep questions here. But we're going to use the center of mass of the canoe, which would be the middle, as the canoe's location. I feel like I've said canoe a lot. All right, with all that, now we can calculate some things. So we essentially need to figure out where is the center of mass here and where is the center of mass there, and then we can figure out how far the boat actually shifted. So our initial center of mass, we have the 100 kilogram person who is 1 meter from our reference point, which we're calling the left end of the canoe. We have the 30 kilogram canoe, which the center of the canoe, okay, because that's where we're using as the canoe's position. Okay, so the center of the canoe is 3 meters from our reference because the canoe is 6 meters long. Now I'm going to divide by total mass. Okay, so about 1.46 meters from the left end. That's where we are initially, center of mass. Final center of mass, so now we have our 100 kilogram person, and he's 5 meters from the left end. The canoe is still 3 meters, so the center of the canoe is still 3 meters from its end. That's not going to change. The only thing that changed is the person. But we can see now the center of mass is at 4.54 meters. So 4.54, yeah, that looks about right. So if he's 5 meters away, it's about, oh, he should be over here. Get over there, bud. There we go. So we can see this is how the center of mass changed, which is how, sorry, said that wrong. This is how far, because the position of the center of mass in space did not change. The reference point did, the canoe did. And the change is going to be the difference in those two, which is 3.08 meters. So the canoe moved 3.08 meters to the left, which is essentially from here to here. That's how much it moved. All right, we're going to do one more problem for this video, and that's going to be two-dimensional center of mass, which is not any more difficult. It's just another step. Oops, wrong color. Neat. All right, so this is best explained just with an example. So say I have a grid and I have a couple different objects at various locations. Here we have -1, 2. So I'm just giving you coordinates of all these. And each one of these points have the same mass. So I have 4 identical masses at different locations. We're going to break this into X and Y. So the horizontal position of the center of mass, we're going to take, just take them each individually. So we'll start with this guy here, just the X direction. Oh, no, we're going to start with, yeah, that's fine. So he's at -1. We have another mass also at -1. We have another mass at 2. We have another mass at 3. And we divide that by the total mass, which is going to be 4 of those m's. So we can see that the m cancels because mass is dumb. So when you take -1 plus -1 plus 2 plus 3 divided by 4, I don't know what my units are, so 0.75. Now I can do the same thing in the y direction. So m times 1 plus m times 2 plus m times 2 plus m times 3, also divided by 4m. Oh, no? Oh, haha, that's negative. That's why. Okay. All right, so we have 1, 2, 3, 4, 5, 6, 7, 6 over 4, 1.5. So the position of the center of mass, I know it's confusing to use X for the overall as well, but we can get over it. Actually, the more better way would be to use the R vector symbol, because that includes both dimensions. Will just be 0.75 comma 1.5. That'd be the easiest way to that. Okay, so 2D, just do your X, do your Y. You just have 2 dimensions to your center of mass.